Okay, welcome back. So, last part, I swear. Let me start just recapping some of the results we were deriving yesterday. So yesterday we spent a lot of time looking at two kinds of topological properties of chemical reaction networks. The first one we considered were conservation laws. And we recognize there are two kinds of conservation laws in an open chemical reaction network. Unbroken conservation laws, they identify pieces of molecules that are carried only by internal species, so they are not exchanged with the environment. And we have broken conservation laws identifying fragments of molecules, moieties, that are carried by the exchange species, so these pieces of molecules are exchanged too with the environment, with the chemostats. And we worked a lot to find a specific representation of these conservation laws, which could identify fragments in such a way that each fragment is exchanged just with one potential chemostat. So we also split the chemostats in potential chemostats, those that exchange one specific fragment, and the force chemostats that are exchanging fragments that were already exchanged with the potential chemostats. So we have an expression for the concentration of these fragments, which can be written in this formal way. And when we take the balance equation, we have that each moiety is exchanged with just one potential chemostat and a bunch of force chemostats. So potential chemostats and force chemostats, they exchange the same moiety, the same fragment. The other topological quantity we considered, we defined cycles, so sequence of reactions such that upon completion, nothing changed for the internal species. And we split them in internal cycles, those that don't change also the chemostatic species, and the emergent cycles, so sequence of reactions that don't change the concentrations, the abundances of the internal species, but do change the concentrations of the chemostatic species. So they basically represent an effective reaction between chemostatic species. But those effective reactions in a mindset where the exchanges with the environment are keeping fixed those concentrations don't affect the total concentration of the species, all right? Okay, for the last part of this course, I would like to use these properties to show you why they are relevant, I would say also crucial, for understanding the energetics of these kind of systems, all right? And I have to start with the blackboard, sorry. So the first property that I would like to show you, it might be a little bit trivial in a way, meaning that I want to show you that for a closed system, right, the Gibbs free energy, the non-equilibrium one, is always lower bounded by the equilibrium one. This, if you want, is trivial because we constructed the equilibrium one to be the minimum, but I want to show you this in a way that actually uses the conservation laws. So I just summarized it. I summarize all the results that I need here also in this part of the blackboard so that I can refer to them. So the way we write our free energy is that G in a non-equilibrium state is the sum over the chemical potentials times the concentrations minus RT times the concentrations. And the equilibrium version is just G at equilibrium is the same, but we evaluated the chemical potentials as well as the concentrations at equilibrium. All right? Now imagine your system is closed, all right? We want to show that in the end, G is always G equilibrium as a lower bound. How do we do that? Well, remember that we have a delta G for every reaction, which is the product of the chemical potentials, the vector of the chemical potential for all the species, and the column of the stoichiometric matrix for reaction rho. Now, at equilibrium, the condition we derived really at the beginning of yesterday morning is that delta G at equilibrium is equal to 0, right, for each reaction. Delta rho G at equilibrium, meaning mu S rho, is equal to 0. And this must be true for every reaction. In other words, mu at equilibrium, scalar product S, is equal to 0. So the chemical potentials at equilibrium are a conservation law. I didn't rewrite the definition, but the conservation laws are the left null eigenvectors of the stoichiometric matrix, right? So we can write the equilibrium chemical potential as a linear combination of conservation laws, okay? Because it belongs to the same space. So in other words, the conservation laws generate the equilibrium chemical potentials. So we can rewrite this term in the equilibrium Gibbs free energy as the scalar product between the equilibrium chemical potentials and the equilibrium concentrations, right? Because here I'm just expressing explicitly the scalar product, the sum over all the species. Now let me write the equilibrium chemical potential as a linear combination of conservation laws. Sum over conservation laws with some coefficients, conservation law lambda, times z. Is that clear? Now, we are assuming we are dealing with a closed system. So by definition of conservation law, this is the concentration of the corresponding moiety, which is conserved in a closed system, because all conservation laws define moieties that are not exchanged with the environment, because the system is closed. Sorry, this is at equilibrium, right? So I can evaluate that quantity for every moment of the dynamics, right? Because it doesn't change in time. So I can rewrite this as the sum over the conservation laws, some coefficients, conservation law, now z at a generic time t, right? But this is still the equilibrium chemical potential. Okay, so z equilibrium, chemical potential at equilibrium times z at equilibrium is equal to actually chemical potential at equilibrium times z at a generic time t. Okay. Now let's take the difference between G and G equilibrium. Here, from what I said, I can just reevaluate these quantities considering the concentrations at the generic time t, the same time of the free energy, of the non-equilibrium free energy, okay? At the same value of the concentrations. So I can rewrite this difference as sum over I, mu I minus mu I equilibrium times Zi. I'm just factorizing out the concentrations. And then I'm left with minus RT Zi minus Zi equilibrium. Okay? Now, if you look back to the expression of the chemical potentials, we have the standard contribution, which is the same independently of whether we are at equilibrium or out of equilibrium. And then we have the log of the concentrations. So in the end, G minus G equilibrium can be written as RT sum over I Zi log Zi over Zi equilibrium minus Zi minus Zi equilibrium. Each one of these contributions along the sum over all the species are positive because, again, of the log inequality. So you have a log of x, you have 1 minus x. The product is always positive. This is 1. And if you can rewrite this term as a product between 1 minus x and log x. And therefore, all contributions are positive. And so G is always lower bounded by G equilibrium in a closed system. Wait. Yeah, okay. This is... Sorry, yes. Thanks for that. Is that okay? So this is a closed system. If you want, it's something we already knew. I'm just exploiting properties that we derived yesterday to show you that G is lower bounded by G equilibrium. And okay, maybe this is not like mind-breaking, but since I'm going to use this strategy of writing the chemical potentials at equilibrium as a linear combination of conservation laws also later on, I think this is like kind of pedagogical to show how can we use them in a simple setup, all right? Okay. Come again? Where's F? No, F is a set of coefficients of my linear combination. Yeah, it's a number. Because I don't know which is the specific linear combination to write down the equilibrium chemical potentials in terms of conservation laws. I just know it's a linear combination because it belongs to the same space. It's not important if you have changes in phases. Why do you say so? So I mean, so the second term in the Gibbs free energy here it comes out from the solvent. No. I mean, okay. Okay, I see what you mean. Yes. If you want, you can interpret it like that. So you can think of it instead of a Gibbs free energy as a Helmholtz free energy, and this is exactly, it would be like P per V. Which is only important when there are big changes of volume. But here we are at constant volume.
But it's only important if the reaction changes the total concentration. Because these terms are total concentration. So that's why there's an analogy. But it's not volume, it's total number, total concentration. Yeah, when total concentration is conserved.
The total concentration is not conserved because you could have non-unimolecular reactions. So like something like A into 2B. Because of that. Yes.
Okay, but if you have all it's all linear, then for linear, you do not see the
May I erase it?
Sorry, just a minor question. The L lambda, so the conservation
Laws.
they are functions of time?
No. They are defined as left null eigenvectors of the stoichiometric matrix. The stoichiometric matrix is time independent. L is time independent. The product between the two is time independent as long as the system is closed. Otherwise, it's time independent only for the unbroken conservation laws. For the MOA, it is carried only by the internal species. Okay. Thank you. Okay, now let me show you why all the pain you went through yesterday is actually useful. So, the way we can write the second law using the Gibbs free energy is the following, as a balanced equation for the entry production. This is the same second law we wrote yesterday. I'm just writing it as a balanced equation for the entry production rate. So we have dissipation on the left-hand side, and on the right-hand side, we have the terms that can balance dissipation. So we have the free energy of the system, so we can dissipate the free energy of the system to stay out of equilibrium. We know that in a closed system, this is lower bounded by equilibrium, so we cannot dissipate it forever. And then we have the terms accounting for how much free energy I can harvest from the environment, right? So how much free energy enters or leaves my system via the exchanges with the environment. Okay, this doesn't tell us much more about an open system that can stay out of equilibrium because I have a source of free energy, which is the environment. Okay, now we're going to use the conservation laws to understand which kind of mechanism can actually maintain the system out of equilibrium. To do so, let me specialize the chemical work, so the work I can extract, exchange with the environment in terms of the contribution of the force species and of the potential species. Right? Yes?
Can you explain again what the
This is sigma dot is the energy reduction rate. It represents the amount of free energy we are dissipating. We are losing it. Right? That's the physical meaning of it. By any process. As long as we are out of equilibrium, something is dissipating free energy. Wasted forever. Okay? So the point is that now we know that what these exchanges with the environment do is to exchange moieties, fragments of molecules, all right? And we know that each potential chemostat is exchanging just one moiety, and that moiety can enter the system, can stay there, or can leave the system via, for example, a force chemostat, okay? So everything we are going to do is just to express the current that is accounting for the moieties, and each moiety is exchanged just with one potential chemostat, and we are going to express it in terms of the concentration of the moiety inside the system and the exchanges with the potential chemostats, right? Let me repeat it. So we have a system. Each potential chemostat is exchanging just one moiety. That fragment can stay inside, or it could be exchanged with force chemostats. Okay, so we are going to express that current in terms of the concentration of the moiety inside and the exchanges with the other chemostats. So I'm just replacing now the current of the exchanges with the potential chemostats in terms of yes, the time derivative of the concentrations of the moieties, so the concentrations of the fragments inside the system, minus the terms accounting for the exchanges with not here, with the force chemostats. Okay, I didn't do anything but expressing I for the potential chemostats in terms of the other two contributions. Okay, now what can I do? I can factorize IF, right? So I can rewrite this as minus time derivative of G. Let me write it like this, plus YF minus lambda broken YP minus 1 lambda broken YF IF. Okay, I'm just factorizing IF for this term and this term, right? Then we are left with the product between the chemical potential of the potential species and the total concentration of the moiety. Okay, now I can write it as minus the time derivative of the chemical potential of the potential species times the current, and then I have the total derivative of this object, which can be included here, minus yp times m. I just took the time derivative, I applied it to both of them, and I'm removing the extra term. Is that clear? Okay, just to be sure. So I have x dt y. I'm writing it as dt xy minus dt x y. and I just absorbing dtxy in here. Okay? And this is actually the final formulation of the second law we can work with. Because now we are going to recognize, just a sec, that this is, we can call this a new free energy. This curly G is different from the original G, not my fault. This is a non-conservative force, non-conservative, and all of this is going to be a non-conservative work rate, and this is a sort of driving work rate. And now I'm going to show you the meaning of the different terms, first in general, and then I'm going to use the example. There was a question, Russ. Yeah, sorry, thanks. Which is also, no, you're right, sorry, yes. YP, so sorry for that, yes. Yes.
Somehow I got lost about the number of copies of rate. So in your first
The copies of?
Rate, 1 over time.
Yes.
First expression, everything has units of 1 over time.
Yes.
Either there's an explicit time derivative or there's a current. In your total derivative for your differentiation by parts term at the end, we have I, which is a current, and then we have d by dt of the chemical potential. This looks like a product of two rates.
Yeah, because I this is not IY, this is M. Oops. Sorry. Let me check if I wrote everything right. Yeah, now it's right. Sorry for that. Really sorry for that. Okay. Are we all here, more or less? Okay. Now let's see what each term means. The first thing that I would like to stress before going through everything is that, okay, this might look a very abstract object for now, okay, but I just want to stress that this quantity would be 0 if there were no force species. Okay, this is a vector with entries corresponding only to the force species. If there were no force species, there would be no chemical potential of the force species. There would be no contribution for the force species due to the conservation laws. So this term is not defined. It doesn't exist if I don't have force species. Okay? So let's look at the first term. We have this new G, which is the Gibbs free energy minus the chemical potential of the potential chemostats times the concentrations of the corresponding moiety. So remember that each potential chemostat is exchanging just one moiety. And here I have the product between each chemical potential and the corresponding concentration of the moiety. So in a way, for those of you who are familiar with a canonical ensemble, it resembles the free energy of a canonical ensemble, right? From the Gibbs of a grand canonical ensemble. From the Gibbs free energy of the canonical one, I'm removing the contribution of the matter exchange with the environment. Now, the other thing I want to show you is that, say I don't have force species. I don't have this contribution. Say I don't derive in time the chemical potential of the potential species, which is controlled by the environment, right? So I can simplify the second law as dT entry production, temperature entry production time derivative of this new Gibbs free energy. This can happen when the system is open and I have only potential species. Right? The system is open, I have only potential species, and I can rewrite the second law in a form in which I have the dissipation and the time derivative of a new free energy. Now, this is something I cannot prove to you today because I don't have time, but this G is always lower bounded. So we cannot dissipate this quantity forever. It means that sooner or later I have to hit a point where the entry production becomes 0. So if our system is open, but we have only potential species, meaning that each chemostat is exchanging just one moiety, and then I don't have another chemostat with which I can exchange the same moiety, that system, despite being open, will reach an equilibrium state. Yes? I'm just assuming that at the moment I'm not driving the chemical potentials of the potential species, right? So in a way, that kind of system has a well-defined equilibrium for every chemical potential of the potential species. For every value of the chemical potential of the potential species, my system, whatever chemical potential I impose from the outside, will eventually reach an equilibrium state. And I don't have to solve the dynamics to say so. I just have to look to the stoichiometry. I see that there are only potential species. If those potential species are not driven, I'm not changing in time their chemical potential, then that system will reach an equilibrium state, and that equilibrium state will depend on those chemical potentials. Now, if I introduce a driving on the chemical potential, now I have this driving now I'm driving the chemical potential of the potential species. From what I told you just a second ago, I have a well-defined equilibrium for each value of the chemical potentials imposed by the outside, as long as I don't have 4 species. So let's keep for a moment the case in which I have 4 species. What does it mean? It means that I'm driving in time the equilibrium state to which my system would like to relax. Okay? Again, for each value of the chemical potentials for the potential species, I have a well-defined equilibrium, and I'm changing that equilibrium in time. The second law becomes something like this. I have this driving, and that driving contribution accounts for the free energy that I'm injecting in the system by changing the equilibrium, and my system is running behind this equilibrium. So it wants to relax towards that equilibrium, but the equilibrium is changing, and if the driving is fast enough, the system will never reach equilibrium, and it will stay out of equilibrium, just because I'm pulling the equilibrium and it's running behind it. I can have as many bath of particles as I want, as long as each chemostat is exchanging just one moiety, which by definition means that I have only potential chemostats. And the problem is that since these fragments are shared between molecules, it's super hard to identify them unless you go through all that pain of yesterday to characterize the topology, the stoichiometry of the network.
Yeah, in this case, how do you create this driving?
So imagine that your system exchanges only glucose. Okay, I have just one chemostatic species that breaks the conservation law, so it's a potential species. And now imagine you are changing the amount of glucose. Okay, that's the only thing your cells can grab from the environment. If I'm changing the glucose concentration, I'm changing the chemical potential of glucose in the environment. I'm changing the chemical potential of the glucose in the cells. I'm driving the equilibrium towards the system is trying to relax. Last point, the final term. This is a non-conservative work, and it's written like mu f minus mu p okay? This term exists only if I have 4 species. If and only if I have species exchanging the same moiety as the potential chemostats, all right? And it's in general different from 0. But what does it mean? Now, let me first give you the intuition, then I'm going to show you that with a derivation. So we are going to see that when the system has only potential species that are chemostated, then the chemical potential of those potential species define the chemical potential of the four species at equilibrium. Okay? So we are choosing, we can choose whatever chemical potential we want for the potential species. The system will relax towards an equilibrium, and at that equilibrium, the chemical potential of the four species is defined by the chemical potential of the potential species. Okay? And this is going to be the equilibrium chemical potential of the four species. So the physical meaning of that force is that I have potential species. They are defined the equilibrium to which the system would relax. They define which chemical potential my moieties have, because that's imposed by the environment, by the potential chemostats. Now, since the force chemostats are exchanging the same moiety, they are applying a different chemical potential to the same fragment. And if that chemical potential doesn't match the equilibrium value imposed by the others, then that creates the non-conservative force maintaining the system out of equilibrium. If you want, for a thermal engine, I have two baths at different temperature, one hot and one cold. One is imposing a temperature towards, and the system would like to equilibrate with that temperature, but the other is imposing another temperature, and so the system doesn't know with which temperature it can relax, and so it cannot relax to any temperature. Okay, this is the same idea. The problem is that it's hard to identify those fragments, those moieties, and that's the reason why we need to go through the conservation laws and blah blah blah, because we need to identify the fragments, those fragments that are exchanged with different chemostats, imposing different chemical potentials to the same particle, if you will. Okay? Yes? No. But then, if you change it, it doesn't change the meaning of that. Meaning, say that you choose one of the force chemostats as potential chemostat and one potential chemostat as force chemostat, then it's the same. It's like saying, I choose the cold reservoir to define an equilibrium to which the system relaxes, and the hot reservoir is the one breaking the existence of the equilibrium. I can do the opposite. I can choose the hot reservoir to define the equilibrium, and the cold reservoir to break the existence of the equilibrium and keeping the system out of equilibrium. Here, it's just more complicated because it's like applying several different baths, and you need to identify the conservation law, the quantity that you are exchanging with many of them. Yes, it's in the way you select the species that break the conservation laws. Yeah, before. But then the point is that, so imagine you have, I'm going to show you that towards the end, you have a huge matrix, you don't know how to deal with that. So you put it in a software, you ask for the conservation laws, you get out a bunch of vectors, and still, the physical meaning is unclear. So you go through that transformation, you identify the potential chemostats and the force chemostats, and then when you get there, you have a physical meaning, and then you can change which one you call potential and which one you call force chemostat. But until you get there and you see which are those fragments, it's very hard to do the same with random vectors.
And maybe emphasize again that the number of potential species and the number
Of broken conservation laws is the same, because one is exchanged with one. I'm gonna, oh yes.
Is it okay to just make a small comment?
Yes, please.
It seems like there's a very nice Legendre dual picture of all of this that in some sense makes it very easy to see. We are used to duality between a concentration and a chemical potential for equilibrium systems. And in your whole broken plus internal
Yes.
system, that's what you have. And then when you add boundary conditions in excess of those compatible with any equilibrium, you wind up with chemical potential differences whose Legendre duals then must become currents because there's nothing left in the space of
Yes.
concentrations for them to be.
Yes.
And how you choose coordinates of that is, of course, up to you.
is the same. Yes. Okay, I'm gonna erase this part just to show you that I'm not bullshitting here, I'm actually telling you the truth. So, from what we just said a few moments ago, blah, blah, blah. Here. So we said that we have the equilibrium chemical potentials, and they are left null eigenvectors of the stoichiometric matrix. So I can write them as a linear combination of conservation laws. Now the thing is that our system is open now. So some conservation laws are broken, some conservation laws are not broken. So we can specialize this sum into unbroken and broken. Because this is still true also with an open system, the condition that the delta G must be equal to 0 for an equilibrium state. That is true whether our system is open or closed. So this is still true. Okay? Now we specialize this for all species. X. Here I'm just taking the X components of the conservation laws. YF, sum over lambda unbroken, F, L unbroken, L unbroken, YF, plus broken, L broken, YF. YP I didn't do anything but rewriting the same thing I wrote before, just I specialize it for the different species and the different kind of conservation laws I have. Now remember that by definition of conservation laws, the unbroken ones are those whose entries for the exchange species, whether they are force or potential species, doesn't matter, but these entries are equal to 0, right? Because the unbroken conservation laws are those that are carried only by the internal species. Okay, so they are not carried by the exchange species. So I don't have those contributions. Is that clear? By definition of unbroken conservation laws, the entries for the exchange species are equal to 0. They are not carried by those species. So let me just rewrite this with a matrix form. I can write it as the vector of these coefficients times the matrix for the broken conservation laws for the 4 species. And then I can do the same here. Okay? Now we have these 3 coefficients. Okay? And now I can choose them as I want. Let me choose them as equal to, I'm making this choice because I know the result. But you can try it and the result is the same. Let me choose them equal to the actual value that the potential chemostats are imposing for the chemical potential of the potential species with a sort of transformation. Okay? I choose, these are 3 coefficients for my equilibrium. Okay? I choose as value the chemical potential of the potential species imposed by the environment. And then when I plug this in, maybe I should have written it somewhere else, but when I plug that in the expression of the chemical potential for the force and the potential species, well, for the potential species you get at equilibrium is mu p lb yp minus 1 lb yp. And this is 1. Is the identity matrix by definition. So the equilibrium chemical potential for the potential species is exactly the one imposed by the outside from the chemostats. If I now plug in this in the expression for the equilibrium chemical potential of the four species, what I get is Yp Yf. So the equilibrium chemical potential for the four species, those that are exchanging the same moieties as the potential chemostats, is univocally defined by the chemical potential of the potential chemostats, and it's exactly this term in the non-conservative force. Is it more or less clear? There are people saying yes. I'm worried about the other people. The other people are silent, so okay. I'll try to show you the example, and then we can go back to it in case. So this is the general expression of the second law that we saw so far. This new Gibbs free energy, the non-conservative work, and the driving. This is the expression of the force that I wrote on the blackboard. This is the identity matrix. It's just because on the blackboard I was a little bit sleepy, but some vectors were row vectors, some vectors were column vectors, and I wasn't paying attention to that because I didn't want to be too picky. But okay, nothing more mysterious than that. It's just that some vectors are rows, some vectors are columns. So let's look how these quantities look like for the example we used during the course. So we chose F and S as potential species. We could have chosen another set. We chose that. So the new free energy is the Gibbs free energy minus the chemical potential of the fuel molecule times the corresponding concentration of the fragment, which is the sum of the concentrations of all molecules carrying that moiety. And then we have the chemical potential of the substrate times the concentration of the fragment carrying the atoms of the substrate. Now the non-conservative forces here are very simple. So we have that the fragment fuel is exchanged exactly with one chemostat and the other. One is imposing the chemical potential of the species fuel, the other is imposing the chemical potential of the species waste. But they are the same fragment, they are the same moiety. So the force is the result of this difference in chemical potentials. Like again, applying to different temperature to the same system. Here we are applying the same a different chemical potential to the same moiety. And the same for substrate and product. Okay? Different chemical potentials, same moiety. The system goes crazy and doesn't know where to relax. It stays out of equilibrium. And these are the non-conservative forces maintaining the system out of equilibrium. And this is the driving accounting for the time variation of the chemical potentials of F and S. Let me repeat all the cases where we have only potential species, we drive the potential species, and then we put the force species. So say we have only, the system is open, we control only the potential species, there's no driving. We don't change F and S in time. Again, from what I told you, there's no driving, there's no non-conservative force. The second law becomes that. Now, I cannot prove you that for a matter of time, but G is always lower bounded, so sooner or later, this system will reach an equilibrium state. Because this is negative, this is decreasing in time until we hit the lower bound, and that must be the equilibrium, because the equilibrium is the only state such that the entropy reduction vanishes. So we can say the system is detail balanced, relaxes to equilibrium without knowing anything about the kinetics, the dynamics. We just need to look at the stoichiometry, the topology. Okay? And I think this is the remarkable result. We have a complex network, we can analyze the stoichiometry and get out whether it's an equilibrium, detail balanced one or not, without knowing anything about the dynamics, the kinetics, the specific kinetic constant, etc., etc., etc. Now imagine that we are driving again the concentrations of fuel and substrate. So there's always a well-defined equilibrium, and the system is trying to relax towards that equilibrium. But if the driving is fast enough, it doesn't reach the equilibrium. So I stay out of equilibrium, and the driving accounts for the amount of energy exchanged with the environment because of the driving of this equilibrium state, because of the change in time of this equilibrium state. Instead now, if I chemostat also the force species W and P, I create a non-conservative force, and unless by chance then the chemical potential of the force species is exactly equal to the chemical potential they would have if I was chemostating only the potential species, unless that happens, I have a non-conservative force keeping the system out of equilibrium. And so I will eventually, for this system, reach a non-equilibrium steady state, where I continuously interconvert fuel into waste, substrate into product. And for that system, which is very simple, this is the only possible state to which you will relax. For more complicated networks, you can have complex behaviors. You can get oscillations. For systems where you consider also the spatial distribution of molecules, you can get patterns, you can get waves, and you can get that only out of equilibrium, as long as you don't have interactions. Otherwise, with interactions, you can have patterns anyway. But if there are no interactions, the only way to create a complex behavior is by having a non-conservative force keeping your system out of equilibrium. Questions? Yes.
So I have questions about, there is a specific choice of representation at some point. So
Yes.
unless you move to something like Eric said, you must have a consistent representation of your phenomenon. But when you make this choice, you must have guarantees that your choice doesn't impact your final relation.
Yeah, it doesn't.
So
Be-
in your FYF,
because in case you change, if you change representation, you change what you call force and what you call potential species, and you change
so ultimately,
which current enters here.
okay, so
But
what
the
terms are invariant is the two last rows must be invariant, which means that your FY
no, you are changing everything. You change G, you change the value of the non-conservative work doesn't change, but you change what's G and what's the driving.
so the non-conservative
Work
work
doesn't
which
change.
means that you must have a relationship between
Yes.
the terms
Yes,
that guarantee
Yes.
that this is always
yes,
verified.
yes.
So what is, do you know
It's because you have this transformation. You are just changing the transformation on both sides.
yes. So this product here,
Yes.
the second term is always the same.
Yes. No. I'm saying that the product between F and I is always the same. It's there that you, because otherwise if you change what the force species are, you are changing also which current you are accounting to account when species are exchanged with the force chemostats, because you are changing the force chemostats.
So I guess there must exist a relation if
Yes.
you change basis.
Yes, that doesn't.
even
Yeah.
invertible
Yes,
matrix, so
yes.
And along these lines, would it be possible then to rewrite that expression in terms of invariance of the matrices, like the determinant, the trace, or?
I never thought about that. So on the top of my head, I wouldn't know how to answer. I guess it could be true, but I.
Because if it is reparameterization invariant, it should be a function of invariance. It might be hard to write down, but
Yeah. Again, I have to think about that. Other questions? Okay.
This freedom is also an asset because depending on what you can measure, you can choose the basis that is more convenient to use.
Yep. Pa-pa-pam. Okay, just want to mention one last thing about non-conservative forces and the way we can use this conservation law. So imagine we are dealing with this system. We have both potential and force chemostats. We reach an equilibrium state, a steady state, which is not an equilibrium state. And at steady state, if we don't drive the concentrations of F and S, we don't have the driving contribution. We are at steady state, so the concentrations don't change in time. The total time derivative of G drops, and we are getting that the dissipation is totally balanced by the non-conservative work. Now, in our system, we have two forces. all right? So we can express the non-conservative work at steady state as the sum of the two contributions. The first force accounting for the fact that we are exchanging F and W with different chemostats, but they are carrying the same moiety times the corresponding current. The same for the second force, resulting from applying different chemical potentials to different species, but carrying the same moiety. Now we have two contributions. There's no reason why both of them must be positive, all right? One of them could be negative. So, and you can interpret one term as an input, so the amount of free energy the system is harvesting from the environment, and the other as an output, the amount of free energy that the system is providing to the environment. And the difference is the dissipation, okay? Now, if you interpret one as an input and the other as an output, like imagine that the first one is the interconversion of nutrients into waste. The second one is the interconversion of ADP into ATP. So we can evaluate the difference between the input, how much energy we get from the nutrients, and how much energy we can store in the ATP. And we can compare the two, and that defines the efficiency of our process. Okay? And that's always between 0 and 1, so because of the entry production rate, and it means, there's a temperature missing there, sorry. And it is a thermodynamic efficiency.
How can you show that it's always bounded?
Because if you rewrite one of the two in terms of the entry production rate, you see that is 1 minus something that is positive. And this is always because if this is 0, you don't have transduction. Okay? And the thing that I would like to stress is that if you interpret this as a force and this is as the resulting current of that force, they're not aligned. So one can be positive and the other negative, unlike what we have for each single elementary reaction, where each delta G is always aligned to each current. Okay? So at this level, where we don't care about all the steps, but we care only about the exchanges with the chemostats, we can get that forces and currents are not aligned, hence we have transduction. So we can use one process which runs in the direction of the thermodynamic force to pull another against the thermodynamic force. So we harvest energy from one process and we spend that energy to do work, to transform a low energy molecule ADP into a high energy molecule ATP. And all of this machinery is to say, how much does it cost? Is it efficient or not? Can I find some kind of guidelines to improve that efficiency? Okay?
But generally speaking, if you have an abstract network, how can you know if one of these terms that you're going to have in the introduction is going to be positive or negative?
Well, you need to quantify those terms. You cannot say it just by looking at the expressions. I'm going to show you examples where we do so. Always numerically, we didn't do, I don't know if Emanuele did it, but okay. No, I think we did it only for examples and specific systems, which are, some of them are quite complicated, related to experiments, but we didn't plug in experimental numbers here. I'm not aware of someone using this formalism. This is the reason why I'm hammering you with this, so maybe you are going to use it one day. Okay. So, further questions? No. Okay, I just want to show you the other way we can rewrite the, yes?
What's the meaning behind the word transduction?
You take a form of energy, if you want, you convert it in a different one. So you take the energy that you gather from, in this case it's always chemical energy, but you transduce the energy stored in fuel, and by processing that energy via the interconversion of fuel into waste, part of it can be harvested and stored in the substrate by interconverting the substrate into the product. like a transfer of energy from one molecule to another. Yes. Okay. No further questions? Okay, I'm gonna be quick with the other formulation of the second law based on cycle, and then I'm gonna go through a bunch of examples, some of them very simple, just to help you sort of like make sense of all the abstract definitions and things I tried to teach you yesterday. And then I'm gonna show you two examples related to experiments, one for synthetic chemistry and the other for biology. All right? So I'm going to show you this second formulation because, like, in the framework of like stochastic thermodynamics, typically people think about cycles rather than conservation laws when dealing with the entry reduction at steady state. So I just want to show you the comparison between the two. Okay, so the general expression of the entry reduction can be written like this, as J, right? Because this is just minus the sum over the delta G of reaction rho times the corresponding current. Okay. Now, let's assume we are a steady state. Now, because we are a steady state, from what we learned yesterday, we can write the current, the vector of all currents at steady state, as a linear combination of cycles. Okay? So let me write this here. Sum over the internal cycles, the currents of the internal cycles, emergent cycles, the currents of the emergent cycles. Now, the internal cycles are, by definition, right null eigenvectors of the stoichiometric matrix. So this doesn't contribute. We are left with the emergent cycles. So we can write this as minus sum over the emergent cycles, mu steady state, S emergent cycle, epsilon. We can specialize this as a contribution for the internal species, and then we have a contribution for the chemostatic species. Okay? Again, emergent cycles are right null eigenvectors of the stoichiometric matrix for the internal cycles. So this disappears. We are left with something that depends only with the chemical potentials of the chemostatic species, those imposed by the environment. Okay? And we can, let me sum up that, write that as sum over the emergent cycle, there's some minus sign, chemical potential of the chemostatic species as chemostatic species, emergent cycle, current. From what I told you yesterday, we can interpret this as the stoichiometry of an effective reaction between chemostatic species. So it's a cycle, so it's a sequence of reaction that doesn't do anything on the internal species, but changes the chemostatic species. Okay, I have a stoichiometry there. So if this is the stoichiometry, then this is the delta G along that effective reaction. And we can simplify the general expression of the entry reduction rate at steady state, which runs over all elementary reactions in terms of a sum of only effective reaction given by the emergent cycles of the delta G of these emergent cycles and the corresponding current. Now, the two second laws look very different, right? We obtain one using conservation laws, rewriting the conservation laws in a different representation, getting out these non-conservative forces. And here we use cycles to get out like a free energy along an effective reactions between chemostatic species. Again, I cannot prove this to you, but there's always a representation where for each emergent cycle, the delta G of that emergent cycle is exactly equal to the non-conservative force of the force species that creates that emergent cycle. Yesterday we saw that potential species break conservation laws, force species create emergent cycles, and there is a representation where each force species that creates an emergent cycle, the delta G corresponding to that emergent cycle is exactly the non-conservative force that we found with the other representation. So these emergent cycles are exactly the processes taking one moiety from one potential chemostat to one force chemostat and creating the non-conservative forces maintaining the system out of equilibrium. Okay, this is the expression of the second law as steady state. As I was saying, if you do that process of computing the emergent cycles for the system we have here, like I showed you yesterday, you get two sequence of reactions. One is pack, 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 so 1F into 1W. So the delta G is the difference between the chemical potential of W and the chemical potential of F, which is exactly, if you remember, the non-conservative force we got out from the analysis based on the conservation laws. If you follow the other cycle, so pack, 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 you get 1S into 1P. The delta G of that effective reaction is again the same non-conservative force that you had in the other description. Okay? Okay, just to sum up the last part, so we derive two kinds of second laws using these topological properties. One based on the conservation laws, and we got out an expression for the forces maintaining the system out of equilibrium. And they emerge only if we have both force and potential chemostats. Because again, they exchange the same moiety, the same object, they apply different chemical potentials, and that creates the force maintaining the system out of equilibrium. We did the same with cycles. So we identified sequence of reactions connecting, if you want, potential and force chemostats. And those reactions are, they create these non-conservative forces again, because along that reaction, since it's an effective reaction, there are only chemostatic species, and from the environment, I'm controlling the chemical potential of those chemostatic species. Okay. If you don't have further questions, I'm gonna go through a bunch of applications just to like retry to do everything in a way quickly, but just to show you. Yes, question.
So maybe I missed it, but is it ever possible that actually the force that maintain the system out of equilibrium is zero, though even if I have both potential?
Yes. Yes. If you choose the chemical potentials of the force species such that is exactly equal to the second part of the force, yes. But it's like saying I'm applying the same temperature with two different thermal reservoirs to an object. I can be in equilibrium there.
So because you say that when I choose the chemical potential of the potential chemostat, then
They
is the one that determines the chemical potential.
the equilibrium chemical potential of the force species. But the chemostats controlling the force species can apply a different one. And when there's this mismatch, that creates the non-conservative forces. If they match, no, you don't have a non-conservative force, even if you are exchanging all of them. Okay. Different presentation. Okay. Example 1. So this is an example with the internal cycle, so you can see also what an internal cycle is. It's a sort of Michaelis-Menten with two intermediates. So you have an enzyme binding the substrate into this complex and then releasing the product. But you can bind it also forming a different complex. Imagine the enzyme, for some weird reasons, has two catalytic sites. Different complex, but you get out the same product. Okay, you can write down the stoichiometric matrix. You can imagine that S and P are exchanged with the environment, and so you have two conservation laws. One for the enzyme, accounting for the atoms of the enzyme, which are shared between the molecule of the enzyme and the two complexes. And then you have a moiety for the substrate. So the atoms of substrate which are shared between the substrate, the two complexes, and the product. Substrate and product, as before, are made of the same atoms. So you can write down, now the matrix for the broken conservation laws is just one row. We can choose S or P as potential species, and the resulting non-conservative force is, again, the difference between the chemical potential that I'm applying to the product and the chemical potential that I'm applying to the substrate. If I do the same with cycles, I get two cycles. One is an internal cycle, so you can see that you can say you go from the enzyme and the substrate to this complex. You release the enzyme and you produce the product. Then you take the enzyme and the product, you go back to the other substrate, and you get out the substrate and the enzyme. If you follow that sequence of reaction, nothing has changed. Both internal species and chemostatic species are restored to their initial concentration. The other cycle is something different. You get S and E, the complex, you release E, and you get out P. So it's an effective reaction going from substrate to product. And the delta G of that reaction is, again, the difference between the chemical potential of the product and the chemical potential of the substrate. Now, I have another bunch of examples, very simple, but I would like, if you don't mind, to go to the application, just to show you that I didn't talk almost 4 hours and a half just for nothing, but there's also something that you can do with actual experiments. Okay, so let me skip. I just want to mention that if you remember sort of like the problem I was showing at the beginning, and the reason why this is a detailed balance system, if you want, you can try to understand it now with the tools that we try to develop in these classes. It's actually more complicated than you can think, even if there is just one reaction. But again, I prefer to do the application. So now imagine you're a chemist, and for your own personal reasons, you want to synthesize an assembled molecule starting from two monomers. All right. However, the free energy of the assembled state is much higher than the standard chemical potential of the monomers. So independently of the kind of pathway that you have that brings you from the monomers to the assembled state, you can have a very complicated one, but sooner or later, if you are in a closed system, you'll get to an equilibrium where the concentration of the monomers is much higher than your target species. Okay, so you're very sad and you say, oh, I didn't do what I wanted to do. And I mean, with this constraint, there's no way around it unless you open the system. And you start exchanging, saying, fuel and waste in a way to drive the reactions and to reach a steady state, which doesn't have to satisfy any constraint about the equivalence between the chemical potential of the monomers and the assembled molecule, all right? And you can reach a steady state which is enriched in your target molecule. The catch is that you have to spend energy to do so. And so, again, everything we did so far is to understand how much energy I have to spend to get to the point where I get the amount of target molecule that I want. And maybe you want to understand it because, I mean, you're spending energy, and maybe you want to understand how much energy you are spending. Are you efficient or not? Can you improve your mechanism? Different pathway can get you to the same point with a different efficiency. So you might want to think about that. Okay, so the first kind of thing you might want to do is just to store a lot of assembled molecule in your system. So if we analyze that system with the tools that I was trying to describe in these lectures, so you have a stoichiometric matrix. I'm going to go fast just because I try to give you the physical meaning, and then you'll see all the steps in the slides. So you have two conservation laws. One is for the monomers, basically, all right? So the atoms composing the monomers and the assembled, and the other is for the fuel and waste. So the monomer, that moiety is carried only by the internal species, the monomers and the assembled molecule. The other conservation law identifies the fragments F, which is carried by these molecules highlighted in green. Okay? When we open the system, so this is the only broken conservation law that we have. And so we have a non-conservative force, which is the difference between the chemical potential applied to the fuel molecule and the chemical potential of the waste molecule. I forgot to say this, but if you want, this mechanism is all about transforming the monomer into an activating monomer, which assembles into an activated assembled species, and then we get out the original target species that we want. And you can plot things like, for example, the concentration of the different species in time when you operate out of equilibrium. And you see that the concentration of the monomer in blue is decreasing, while the concentration of your target species in red is increasing. And you can try to understand the concentrations at steady state for different values of this non-conservative force, trying to understand how much of your target species you get depending on how far from equilibrium you are. So say you set your force to 0, okay? And the most concentrated species is the monomer, the blue line here. And one of the least concentrated species is your target species. Very sad. You start moving out of equilibrium, and you are decreasing the concentration of monomer that you get at steady state, the blue line. Here I'm showing the different steady state concentrations for different value of the force, the non-conservative force keeping the system out of equilibrium. And I can reach to a point where I have a maximum, here in red, of the concentration of my target species, and I minimize the concentration of my monomers. Okay, and I do that out of equilibrium, and I cannot maximize any further, and I can reach that point only if I apply that non-conservative force. Okay, now to evaluate the efficiency of that process, what are you doing? You are storing energy inside your system, and you are spending energy to do so. So actually, here you can compare the amount of free energy with the amount of energy you are providing to the system. However, you reach always a steady state where the concentration of your target molecule doesn't increase any further. But you have to stay out of equilibrium to maintain that concentration. So you see that in time, you are increasing the free energy of your system by spending energy, here this dashed blue line. But in the end, the energy that you stored in your system doesn't change anymore, because you saturated the amount of species you can create, but you are still spending energy. The dashed line is increasing. This is integrated in time, okay? It's increasing because I'm still spending energy to maintain the system out of equilibrium. So my efficiency is actually dropping. Yes?
To increase the concentration of A2, it's not enough just to couple A2 with F and W without these cycles.
Yeah, that's the next step. The next step to avoid is like storage of energy, but to maintain that storage of energy, you have to continuously spend energy. You can start extracting A2 and injecting the monomer continuously. So you put in the reactants and you extract your target species.
No, I was mentioning it just to couple just one reaction, A2 and
Yeah.
F plus F goes to A2 plus W. That's it.
Come again? But okay. You say I have a different mechanism here. So completely different reactions. Yeah, okay, but that's depend on the kind of system you're dealing with. This is sort of given by the experiment, if you will. So now you break also the other conservation laws, the one accounting for the moiety of the monomer. Okay, so you create two non-conservative forces, one accounting for the input of free energy by converting fuel into waste, and the other accounting for the output of free energy by converting monomer, a low energy molecule, into the assembled molecule, A2. And you can look, for example, at the different value of the efficiency for different value of the non-conservative force applied to fuel and waste, and the kinetic constant at which you are extracting the target molecule. Okay? And there is a region here where there's a maximum of your efficiency. And you can compare that efficiency with the output power. So how much free energy I'm just extracting. And the point is that when you are close to equilibrium, so low extraction rates and small non-conservative forces, the power that you are extracting and the efficiency never cross. While here, maybe you don't see it very clearly, but here there's a point where the orange line representing the condition at which you are operating at maximum power crosses with the line, the yellow dashed line, representing the conditions at which you are getting the maximum efficiency. So there's a point where you have maximum efficiency and maximum output power. And you can find that point only if you have a thermodynamic structure telling you the energetics, how much energy you are putting in, how much energy you are putting out, and how efficient you are. Okay, but this is a school about biology. So I have also, okay, this is just what I said, an example about a biological system. So we actually studied, no, I have two examples, but I'm gonna skip the first one. Sorry. Okay, because Massi cares about that one very much. I'm gonna go to the second one. I had two examples, but for the sake of time, I'm gonna show you just the second one. So the second one, we studied, if you want, a mitochondrium, so the TCA cycle inside the mitochondrium, and we studied it as it was a chemical engine, interconverting nutrients into waste, ADP into ATP, when it's coupled to calcium oscillations in the cytosol. Because calcium can trigger some steps of the TCA cycle and increase the rate of some steps because it interacts with some enzymes along the TCA cycles. So we had a very complicated model where all these colored boxes in the drawing, they are actually effective reactions, okay? They are coarse-grained reactions. So everything I try to teach you during the lessons is based on having elementary reactions, but we have ways to deal also with effective reactions, right? So all of these colored boxes are effective reactions, but then you can apply the same recipe that I taught you, I tried to teach you, to the system where you have effective reactions, right? And if you analyze the system like that, you get that stoichiometric matrix. Now, maybe you want to understand which are the moieties starting from the drawing, but it's very hard. And if you look at the stoichiometric matrix, it's even harder. So that's the reason why yesterday I spent so much time hammering you with all that procedure to analyze the conservation laws. Because if you're dealing with a matrix even bigger than this one, because this is relatively small, well, you get out random conservation laws, you don't know what to do with them, and then you have to go through that transformation to understand which fragments, which moieties you are dealing with. All right? Yeah, this is just a remark. And I just want to try to justify myself, so explaining the reasons why I went through all of that, because try to understand which non-conservative forces you have just by looking at the stoichiometric matrix, so by looking at the drawings, you're going to be lost in a second. And so you need a sort of recipe which looks hard to understand, but it's just math if you want. It's just linear algebra. And when you get the sense of it, you can deal with any system you want as long as your computer is powerful enough to deal with the stoichiometry. And if you do so, you end up with basically 3 effective reactions between chemostatic species, and one can be interpreted as an output, the others as input, and you can define an efficiency also when you have these oscillations of calcium, and you can compute, for example, the efficiency when you change the control parameter triggering these calcium oscillations in the cytosol, affecting the enzyme kinetics in the TCA cycle. And you have a very weird behavior where at steady state the efficiency is dropping, and as soon as the calcium oscillations are kicking in, you get an increase in the efficiency. All right? But about the biological implication of all of this, Alex is going to talk about it on Friday, I think. Okay. The color is just like the frequency of the waves. Right. Okay, this is it. I'm done torturing you. I just want to mention that I try to give you like the basics of what the group in Luxembourg developed over the years, so that you could, if you are interested, understand also maybe other follow-ups. But the group really worked on many things, and so just to advertise the other things, there are a lot of papers. They are not all of them are not mine. Okay, I don't publish so much, but I mean there are a lot of work that has been done from the ideal situation that I tried to use because I thought it was more pedagogical. There are works on that generalize it beyond ideal systems where you have interactions. We contributed also to understand the energetics when you have diffusion, when the diffusion is also with species interacting, so you don't understand whether interactions or non-equilibrium reactions are actually maintaining the non-homogeneous state. We worked with some of us, not me, I'm not good enough to do that, with experimentalists to understand specific molecular motors they designed. We worked on the transduction, as I was mentioning before, in metabolism, the two examples I was mentioning. We have works in understanding how to simplify a very complicated network where we cannot track down all the elementary reactions, and also something about the processing of information in chemical reaction networks. Done. 12:30. Thanks.